In this video, we want to be lazy/efficient when we are looking at solutions to Maxwell's equations. So say we're dealing with the eigenvalue problem that we've been studying so far, namely theta h is equal to omega squared mu of h. And you're a little bit too lazy to solve this eigenvalue problem exactly, numerically, whatever. But you still want to be able to make some sort of broad general statements about types, families of solutions that could exist based on the symmetry of the system. So this is our goal, trying to figure out whether we can make such statements without actually solving the eigenvalue problem directly based on symmetry. Before we do that, it's worth defining what exactly we mean by symmetry. So what does it mean if we have a system that has a certain symmetry? So for example, this circle here, you rotate this circle over a certain angle and you basically end up with exactly the same circle. This is why we say that symmetry basically means if you have a coordinate transformation, a certain coordinate transformation that takes you from R to R prime, and if that coordinate transformation leaves your system intact, then you have a certain symmetry. Now in our case for Maxwell, the structures that we're interested in are described by epsilon as a function of R, which is then encoded, of course, in our theta operator. Epsilon is hidden somewhere inside this theta operator. So this is where the potential symmetry is encoded in this distribution of the refractive index. And we could have rotational symmetry, as we have here, but there's, of course, many other types of symmetries. There's mirror symmetry. If you flip here over this mirror axis, you also end up with the same structure. If you have a waveguide like this, for example, and you translate that over a certain distance, then you also end up with the same structure. So this is translational symmetry. So these are all examples of different types of symmetries. And the question is, how does the existence of these symmetries affect different types of families, different types of solutions that we have within Maxwell's equations? Now, as an example in this video, we're going to use yet another symmetry, and that's the so-called inversion symmetry. If we have our origin over here, and if we have a cavity that looks, for example, something like this, and the first question we could ask ourselves is, what is the coordinate transformation that leaves this system intact? So pause the video and see if you can identify the transformation that corresponds to the inversion symmetry here. Not so difficult to see that if you have a certain vector r here, and if you replace that with minus r, then you end up with exactly the same cavity. So here, the transformation that we're looking at is that r prime is equal to minus r minus the original r. Okay. So we've identified that our system has a certain symmetry. We've identified the coordinate transformation that goes with that. And let's say that we have a certain solution h of r that is a solution to our eigenvalue problem, which has a certain eigenvalue omega squared mu. Okay. What is then the consequence of the fact that the system is invariant under this coordinate transformation related to that solution h of r that we already have? Pause the video and think about this. Your first instinct might be to say that since we have r replacing by minus r doesn't change anything, that would also mean that h of minus r will be the same as h of r. But as we will see later on, that's a little bit too premature. But something we can say without any problem is that if h of r is a solution with eigenvalue omega squared mu, then it also has to be the case that h of minus r is also a solution with exactly the same eigenvalue, simply because of the fact that the cavity cannot tell r from minus r apart. What exactly the relationship is between h of r and h of minus r, that's something we will be thinking about in the near future. But of course, so far, there's nothing wrong with saying that if h of r is a solution, certainly h of minus r should also be a solution. The next step we're going to take is we're going to make a restriction, and that restriction is that we're dealing with situations where there's no degeneracy. So pause the video and think about the consequence of the fact that we restrict ourselves to situations where the solutions are not degenerate. Recall the definition of degeneracy. Degeneracy means that if you have a certain frequency omega, it's possible that there are two completely different solutions there at that frequency omega. But here we exclude that situation. So this means that if we're looking at a certain frequency omega here, that there can only be one single possible solution. So how do we reconcile this with the fact that both h of r and h of minus r are a solution at frequency omega because of symmetry? So how do we reconcile these two pieces of information? Well, this means that the inescapable conclusion is that h of r and h of minus r are actually the same solution, the same mode. So you might be tempted to write down then that this means that h of minus r is equal to h of r, exactly. But that would be wrong, because remember, these modes, these solutions, they are only defined up to a proportionality constant. So we can multiply this with alpha and still end up with what we essentially call the same mode. When we talk about degeneracy, we're not talking about this trivial scaling here that you can do with any mode. So saying that h of r and h of minus r correspond to the same mode basically means that they're related here with a simple scaling factor alpha. Right? Let's now take the next step and let's try to invert the system again. So if we invert the system once and then one more time, we end up with the original system. So see if based on this, you can gain some extra information about possible values for alpha. So if we invert the system twice, then we basically can look at h of minus r, right? So we know from this statement over here that we can get rid of this minus sign here if we pay a certain price, which is multiplication by this factor alpha. So let's get rid of this first minus sign to give us h of minus r, and then the price we pay is an extra factor of alpha. We can play that game one more time, this time getting rid of this minus sign and paying yet another factor of alpha. So now we have then alpha squared h of r. But if you look again at the left-hand side, minus r, that's of course just simply r. And if we bring everything together, basically means that alpha squared here should be equal to 1. So that's the inescapable conclusion here, alpha squared equal to 1. And this means that there's basically two possible cases that we can study here. One case is where alpha is equal to 1. That was the naive thing that you would think of first, namely that h of minus r is equal to h of r. And that would correspond to a situation where, for example, if you have a positive phase over here, you would also have a positive phase over there. And these are the so-called even solutions of our problem. But we see here is that there's also another distinct possibility, namely that h of minus r is equal to minus h of r. And if we then make a drawing, basically means that the phase flips, so the plus becomes a minus, and these are then odd solutions. So what we've seen so far is that without solving Maxwell's equations explicitly, we know that if our system has inversion symmetry, and if it turns out that there's no degeneracy in the system, then the solutions fall in two different classes, either even solutions or odd solutions. Of course, the white elephant in the room here is perhaps this overly restrictive situation where we only deal with the fact that we don't have degeneracy, because this was a really crucial ingredient in coming up with our argument here. So you might wonder what happens if we do have degeneracy, because this happens, of course, from time to time in real systems. And then it turns out that you can prove, I'm not going to do that here, that if you have degeneracy, then The conclusion is not that you either have even modes or odd modes automatically, but the conclusion is that it will always be possible to make linear solutions, linear combinations of two solutions that you have, such that the linear combinations of those, that they are either even or odd. So you can't guarantee that if you have degeneracy, that any arbitrary solution that you find will be even or odd. But if you find two of them which are different, then it will be possible to make linear combinations of those, and these then will be even or odd. So that's a small footnote for the case where we do have degeneracy.